acceleration. Right? Like when I said, is there acceleration going on right now? Your pre-AP answer would be, is there acceleration going on right now?
Yes. Yeah.
Your AP experience is yes, but your
you
pre-AP, you'd be like,
No.
no.
Same speed.
Yeah, same speed, there's no acceleration. So there's some of it that sort of like required your mind to think, okay, I need to re-understand what, or understand the proper physics definition of acceleration is. And we're going to kind of have a little bit of that with energy and work and also power. There's some of this stuff that's going to be like potential energy, got it, I've known that all along. Kinetic energy, got it. But we will talk about like positive work and negative work, and that sometimes sends students a little bit into like a, no, this doesn't totally feel right. So we're also, in this chapter, going to be exposed to a new way of thinking about problems. Okay, so we're not going to be just locked in on kinematics and dynamics and momentum and impulse. We're also going to be able to look at, we're also going to be figuring out or learning a new problem-solving strategy. Bill, if you don't mind, you put that up. Thank you. All right. So I think in your maybe earlier science classes, kinetic energy, y'all have heard about that stuff, potential energy. Just gut level, what's kinetic energy? Motion, something's moving, something's, okay, what about potential energy?
It's when the object has the potential, but it's not moving.
Okay, yeah, like it could be moving, somehow stored. There's also thermal energy. That's another one we're going to be talking about. And physics is interested in the transformation of that energy from potential to kinetic, or maybe from kinetic to potential. For instance, right now this ball sitting there at the table, we could say has 0 potential energy. Okay, now it's got kinetic energy, but up here now it has that. It has potential. That kinetic energy that I've used to move that is now turned into potential energy. So when you're putting energy into a system or taking energy out, for instance, right now this ball has lots of potential energy, but no kinetic energy. All right. For that moment when it was falling, it had kinetic energy. We would say that work was being done on the ball. Okay, so. We'll be talking about this thing called work and what that means. And that's one of those things, sometimes it matches what you expect and sometimes it doesn't. All right. Energy also, there's a conservation law with energy, just like there was momentum. This is our second conservation of energy, or conservation law, so we'll find out about that. All right. So let's get going. So the basic energy model of a system, we can break, if we're looking at an object or a pair of objects or dozens of objects or whatever, what we want to do is we want to define what is in that grouping and then what is outside of that grouping. And that grouping is what's called a system. So within a given system, you can break down and identify all the different types of energy that are in there. And we have a symbol for each one of them. K is for kinetic. UG, the U in general is potential. UG is gravitational potential. It'd be nice if it was a big P, but we use big P for power. This is potential, but with a spring, hence the S. This is thermal energy, the E and the TH for thermal. Chemical energy, you can have nuclear energy, other things like that. We are not going to be talking so much about the chemical and the nuclear. All right? So what we use just sort of the generic capital E is to represent all of those different energies combined. And we would say that's the total energy of that system. Okay? So we could be talking about the ball and the earth and the total energy of the ball-earth system. Or, since I'm actually a part of this at this point, you can talk about the Mr. Goddard ball-earth system and what's the kinetic, potential, thermal energy of all those. All right, so some of y'all mentioned kinetic energy. That's energy of motion. When something is moving, we say it has kinetic energy. Gravitational potential energy is stored it's associated with the object's height above the ground, okay? And when we dig into this a little bit deeper, we'll find out that you can kind of make the decision where ground is. Like, what is the zero level? Just sort of like when we were solving our problems, remember we always determined where the origin was. Is the origin over here, or is the origin over here? And you can kind of make your decision based on what was, helpful for you. Okay? If the ball is sitting there on the table, we've got some choices. You could say that zero potential energy is right there on the table, which is great if I'm going to be moving up and down along here relative to the table. We could also describe that potential energy, the zero level, is at the ground floor. Okay? In which case, at this moment right now, the ball has potential energy, right? If I say that the ground is the zero level, then in order for me to pull it up here, I've got to add energy to that system, and so now that ball has potential energy. Okay? So if I pull it up here, it has even more potential energy, right? But we can determine where we want the zero level to be for any given particular problem. Now you might say, it doesn't have any potential energy. It's not going to fall anywhere. Potential energy might be like if you're holding it just like this. Well, no. Potential energy depends on the height. It does not depend on the manner in which it's held or anything like that. Okay? It also depends on the mass. Spring or potential energy is when you've got, I've got my slinkies back there. I mean, throw me that slinky. So that's when you have energy. Just go and toss it to me. Thanks. In the spring, so if I stretch this out and I let it go, right now it has potential energy, and now it doesn't have any potential energy.
But while it was moving, it had kinetic.
While it was moving, it had kinetic. In fact, while it was moving, the potential energy was decreasing and the kinetic energy was increasing. All right?
So it's like what could happen?
Like potential energy is like what could happen?
Yeah. You haven't.
No, I wouldn't say it's what could happen in that way exactly. Because you think about what could happen, you'd be like, well, this could explode randomly or something like that. You get into like theoretical stuff. It's better off to say, I mean, if there is potential energy, then there's some force or there's something that is preventing that potential energy from becoming actual kinetic energy, right? For instance, right now, if we describe the zero level for potential energy as the ground, there is something preventing this ball from that potential energy turning into kinetic, and it's the stool pushing up on it. Okay, that's forming the same thing as this hand over here holding the spring out. And then I let it go, and it comes back. So, but I kind of know what you're saying there. Thermal energy is the sum of the kinetic and potential energies of all of the molecules in an object. So one way that we'll talk about thermal energy and friction is, if you rub your hands together, what happens is that you move those molecules around a lot more. They're rubbing against each other and they're bumping and jiggling and doing all sorts of stuff, and so therefore you get more thermal energy. Chemical energy is stored in the chemical bonds. That's more of like a chemistry thing. So let's kind of say high chemical energy and biochemical energy. And then same thing with nuclear energy. If we took the AP Physics 2, then we would talk about that. Maybe after the AP test, we'll read 1 or 2 chapters on that. But that's not really our concern at this point. So energy can be transformed into energy of another kind, like we were seeing a minute ago with the spring. You can have kinetic turn into potential, or potential turn into kinetic, and this is just potential, like gravitational potential energy or spring potential energy. Those can turn to chemical or back and forth. And then there can be thermal, like for instance, when you move your hands together like that, you are turning that kinetic energy into thermal energy, all right? And like I said, this is all contained within the system, whatever we define the system to be. And
have two systems and a bigger system?
Yes, but then you would just say,
Then
you
go-
would, technically you just,
One.
you'd have one big system. You have multiple objects within a system. Yep. So the book kind of talks through different transformations. For instance, there's chemical energy in the weightlifter, and then turning that into gravitational potential as she lifts the bar there. All right. We've got elastic potential here in the diving board, which will turn into kinetic as the diver is tossed into the air. All right. Let's see. Before we go to this, let me give you a few more. Well, I guess we'll answer this question. We'll go piece by piece. Go ahead. These first two questions, go ahead and answer those while I take attendance.
Would you draw these on a free body diagram, like the energy?
Energy. No, free body. Good question. Free body diagrams are for forces only. This is energy. It's a different way of looking at the problem.
Energy is caused by force, but it's not.
We are good. That is correct. Energy is not a force. It's a new thing. In a minute, we're going to talk about how energy relates to forces.
Is energy what creates forces?
Right there.
No,
Oh, but the-
energy. It's a. What creates forces is like.
Okay.
Your desire for there to be a force.
Because
I mean,
it looks like a.
you know what I'm saying? Energy is something different.
Okay.
Go ahead and answer those first two questions.
What's potential? Gravitational potential. Oh, it's due to. It's V. It's due to kinetic.
Yeah, because gravity here.
I think this
This
is
next
slope.
one after this one.
But it's already gliding down.
She's not making friction on the ground. She's making destruction.
I don't know.
Back down.
What's
It never
ETA?
says that she's not gonna stop or any that stops. There's never be potential energy.
What is he?
Although like gravity is
And
she's
now
running on the hill.
He's motionless.
Well, yeah.
Yeah, she's already in motion in the time that she analyzes it.
I'm sorry.
So we're not
So when it be fun, she's having making even though it's snow, she's like making
Oh, but I
you know, she's like picture clear on her skis.
So wait, what about the other one? That's the other one.
Like
And the other
Doesn't
one.
say speed. It doesn't say.
It doesn't say
stop.
stop.
Yeah.
That's
I
the
think-
thing. It's just
yeah.
like, what's ETA?
And you
Thermal.
oh.
Oh, isn't it thermal? Isn't it creating like while it's going down, isn't it creating heat?
I mean,
Here's
Think about
the
it.
swing.
I
Yeah.
guess.
If you decide a calculator here, it would create heat.
Alright, so this one, you got the kid at the top, motionless
Hold on a second.
at the point of the, and then he's gonna swing down.
Okay, but he's swinging down now.
This says, what energy transformation takes place as he swings back down to the lowest point, okay? So, what sort of energy does the child have at the top?
Potential.
Potential,
Gravitation.
gravitational. He's not moving at all. So therefore, the kinetic energy is zero. Potential energy is some number, we don't know what it happens to be. What about at the bottom of the swing? Potential gravitational energy is, we're gonna say zero. Now you might say, well, not entirely, because the kid could fall off the swing and then he'd be, you know, so he's got some
Let's
potential.
pretend he's touching the floor.
Right, okay, yeah, we can pretend that his feet hit the ground. Or we could just define this level right here as the zero level.
Yeah, no.
So at this point, gravitational potential is zero. It's not gonna do any work on the system. The kinetic energy is everything, it's all. Alright, so here we're going gravitational potential to kinetic. Now, technically, some of it is also transferred to thermal. Because if you've ever been on a swing and you go to the highest point, and then you go, and then you come back, and you don't pump your legs or anything like that, do you go as high?
No.
No, you don't go as high. Because, especially if you've got really creaky, squeaky hinges up here at the top, yeah, it's not gonna, some of that energy from your potential to kinetic all the way back up here, and then by the time you get back over here, some of that has heated up that hinge just a little bit, okay? And we'd be able to see that if we had a thermal imaging camera, which would be cool to have. All right.
Next one.
A skier is gliding down a gentle slope at a constant speed. What energy transformation is taking place?
My slope is invented.
So, here's the skier with the skis. The skis have they're kind of tipped up a little bit, in case you didn't know that. So, and they've got the poles with little things around there. They should have the poles at the top.
Put that on.
And you got a little beanie right there. There's also they should be holding the poles at
Sure,
the
I've seen
ends,
the
but
back.
that's okay. So as they're going down at a constant speed, what energy transformation is taking place? What did y'all say?
I would-
Kinetic
The
to
thermal.
Wait, is it kinetic to thermal?
Kinetic to thermal?
We didn't know if it was kinetic to thermal or gravity
Yeah.
to kinetic.
Yeah.
I could be.
Because he's
With-
already moving.
Yeah, if you say he is, yeah, this is not one of my favorite problems, okay? Because let's change it a little bit. Let's say that skier starts at the top.
But then that changes the question completely, doesn't it?
I know, that's why I don't like it as. Has a constant velocity down the slope, and then they ends up at the bottom down here. Okay. Now, one of the things, and I don't know how they expect you to know this at this point, is that excuse me, the kinetic energy, we'll find out, is 1/2 mass times the velocity squared. We'll find out later on, there's a formula for gravitational potential energy. It's the mass times the acceleration due to gravity times the change in height. So, as we're going from this point up here down to this point down here, all of this potential energy has now transformed into, you might say, might turn into kinetic energy, because they're moving, yeah, as they are, but some of it also is turning into thermal energy, okay? Even though it's snow, and even though it is pretty slippery, there's still friction during that entire time, okay? So we would say that gravitational potential energy, and when they're right here, some of that gravitational potential energy is now kinetic, and some of it is also thermal. So I'm not a real big fan.
Wouldn't it just be thermal? Because it's the sum of the kinetic and potential energies.
It's the sum of the, read the rest of the part.
Energies of all the molecules in an object.
Right, of all the different particles of everything kind of moving around here, okay? Now,
So the answer would be B and E.
of my modified question, we would say potential if we're looking from here to here, the potential energy turns into kinetic and thermal. Now that's not what they were trying to get at. You would tell you what they're trying to do. This is what they were trying to do. They were saying from the moment that he's right here to the moment that he's right here. Okay? Because the skier is gliding down a gentle slope at a constant speed. So this is what they were trying to get at. So if we look at it from this moment to this moment, kinetic energy here is 1/2 mv squared. The kinetic energy here is 1/2 mv squared. And since we're going at a constant speed, has the mass changed? Has the velocity changed? No. So there's no new kinetic energy from here to here if he's going at a constant speed. So therefore, we do notice that he was a little bit higher right here than he was here. So there is a transformation of the gravitational potential energy into thermal.
Oh, it was both lessons together.
Right. But it's an ambiguous question because they need to clearly identify, in my opinion, what's the beginning point, what's the end point, and so therefore what the transformation is. You could have interpreted this as from up here down to there. So, bottom line, if you're looking at them from, ladies, from point on the slope to point on the slope, then it's gravitational has turned into thermal. If you're looking at it from standing on the top of the hill to down here, then all of that gravitational has turned into kinetic and thermal. But that's why you'll see that one right there for their answer. Like I said, I'm not really a big fan of that question in that order. Okay, so we've got the system. Can anything break through into that system? Sure. In fact, if you have energy going into a system or leaving a system, then that is called work or heat. They can go either way. You can put work into the system or heat. So you have energy transferred from the environment to the system, or energy transferred from the system out into the environment. And you say, okay, well, is work only the stuff that goes in and heat the only stuff that comes out? No, that's a bad picture on their part. Work is the mechanical transfer of energy to or from a system by pushing or pulling on it, okay? And so work can go in or out. Either you can have the system, like for instance, we'll say the system is just the ball and the stool, okay, and the earth, all right? I am now outside of the system. I'm going to do some work on that, okay? And I am changing the energy of that whole entire system, okay? So that's me doing that. Also, heat is the non-mechanical transfer. So that's something that's not pushing or pulling. It's by changing the temperature the difference, or the changing temperature value. And that can go either into the system or out of the system. It doesn't have to be just coming out, all right? So you can think if this system was like a furnace or whatever, okay, and you're only considering the furnace as the system, you have the chemical energy from the logs turning into thermal energy, okay, in the terms of the heat, okay, but you'll notice that furnace, even if you draw an imaginary circle, you know, around that furnace, it's going to be interacting with the air around it, and heat is going to be leaving this system. And you can think of it just, you know, the other way around. If your system is the oven, but you don't count anything in it, you know, the oven's really hot. It's turning electrical or the chemical energy from gas. It's turning that into heat energy, and then that, you know, like that's the system. Then over here you've got your food, your pizza or whatever. Okay, this energy is leaving the oven and going into the food, or you circle the food. You can have heat going in. So anyway, the idea is that heat and work is energy coming into or out of the system. So this says the athlete does work on the shot, giving it kinetic energy. I would might add, so if you consider the shot in isolation, then him doing some force on it, moving it mechanically, would be him adding energy to the system. And since it's actually moving, we would call that additional energy work. So, oh, that boy is shooting at the cameraman, apparently. Alright, the boy does work on the slingshot. So if you're to draw a circle around the slingshot with the rubber bands, we'd say that's the system, okay? The boy is going to reach into that system and add some energy, because sitting by itself, the rubber band's not going to do anything, okay? But then he changes the energy. That changing of the energy is what's called work, okay? He's changing the energy of the system mechanically, so that's why we call it work. All right, so I think you've got another problem here. A tow rope pulls a skier, once you get that skier here, up the slope at a constant speed. What energy transfer is taking place?
Attention. Because he could fall.
Oh, yeah, cause if you're increasing the speed, and not the speed, but the distance, the height, increasing the speed. It's not increasing kinetic because it's going at constant speed.
That is correct, Emily. His velocity is not changing, and so therefore there's no additional kinetic energy.
I would assume it's
Because he's also,
We're looking at it from that moment right there to that moment right there, okay, on the slope. So the tow rope, which is pulling him up, is, whoops, holding on to it. Anyway, so it's holding on to that rope. That tow rope is pulling him. It's changing the thermal energy between the skis and the snow, and it's changing his gravitational potential energy, because we can see it's going to be higher there. All right, so that's a really long formula right there, but this is what you need to know. I think it's on your AP chart. So pull your chart out. Is that on your formula chart? Yeah, there's some other things on it too. This is the first idea. They want to kind of put everything all on the same line. All right, so if you have your system, and then outside you have the environment, any change in energy within that system's either going to be having more energy thrown into it or energy leaving it, okay? So if there's any change in that system, that means you've either got stuff coming in, energy coming in, or energy going out. And so you're going to have a change in energy. If the total energy of the system was 10 joules, okay, and now you have 11 joules in there, that's because there was some work that was done on the system that's added more energy. If it's changed from 10 down to 5, that means 5 joules have left the system, okay? And that means the system has done some work on something else. So that's why we say the change in the energy of a system is equal to the work done. It's either work done on the system or work done by the system on the environment. If there's no energy transferred, then we call that an isolated system. Okay. So here we go. Crane lowers a girder into place at a constant speed. Consider the work done by gravity and the work done by the tension in the cable. Which of these is true? One of them is positive, one of them is negative, or they're both positive, both negative, or they're both equal to 0. Let's draw a picture.
He's getting closer.
Alright, now that makes a lot more sense. Here's the error. And so this thing happens to be lowering. So we've got some velocity. Alright. What's going on if we just consider the Earth girder system? So, Earth girder, tension in the rope, okay? As this thing is lowering, talk to me about the energy. As it's getting closer and closer to the Earth.
The
potential
gravity
energy
potential is
less.
Decreasing, okay, so there's less and less energy, right?
Yeah.
Okay. So, so that's kind of like this is our system and it's going down, right? So there's less energy. What's causing that drop in energy? Gravity. Okay?
Okay.
So we could say, so it makes sense that if gravity is causing the decrease, then the work done by gravity
Greater.
is positive.
Oh.
Okay? Gravity's doing work on the system. Okay? What about the tension? Is that doing anything? No. Well, it's preventing it. It's
against the gravity.
it's going against the gravity.
So that's negative.
Yes. So the work done by tension is negative. I should be consistent. I should put minus. All right. So it says the downward force of gravity is in the direction of motion. Positive work, upward tension. Now, I don't know about you, but I don't like that. I'm like, okay, that seems kind of fuzzy. Let me give you something that's a little bit more solid, okay? Work can be positive and work can be negative. And this is the part that's not so obvious, but I'll make it real obvious for you this way. If the force is in the same direction as the motion, then that force is doing work on the system. In fact, it's doing positive work on the system.
That makes more sense.
Because you think of it, do a little horizontal explanation. I'm going to be, if you consider the system of the stool right there, and I'm going to put some force on it, right? And the direction that it's moving is the direction that the force that I'm pushing, okay? Then I'm actually, we think he's moving it. It has kinetic energy now. I've added energy to the system because what I'm doing is directly resulting in that motion. Okay, so my push or pull, my force is positive work on the system, and so therefore that's going to increase the overall energy of that system. Negative work occurs when a force that is being applied on a system is in the opposite direction of the motion. of the system. That gives you negative work.
Do the same rules apply for heat? Or do they look different?
Well, you don't have direction
There's heat.
of motion with heat. Something can just be sitting there and getting heated up.
Oh.
So it does not really apply. Now, contemplating this, what's the direction of the gravitational force? Downward. What's the motion of the beam? Downward. So therefore gravity is doing positive work since they're both going, since it's moving in the direction of that force. What about the tension? What's the direction of the tension? Up. What's the direction of the motion? Down. So we would say that tension is doing negative work on the system. Okay? It's kind of weird to think about negative work on the system, but that's the way that we would think about it.
It makes more sense than negative loss you did the first week.
That's okay, that's true. Alright, so here we go, you turn your paper over. Robert pushes the box to the left at a constant speed. In doing so, Robert does positive work, okay? Now, let's say there's somebody else over here that's also doing some pushing, okay?
But it's still going up.
His name is Mosley. And he is pushing this way. However, the box is moving in that direction.
So it's negative.
We would say that Mosley is doing negative work on the box.
I don't know, the box was a stick.
I guess maybe if you think about it like this, positive work is where like I'm pushing on this, and so it's moving. It's like I'm adding more energy to the system. Will you play Mosley? So if positive work is me putting energy into the system, negative work would be taking it out, or the system doing energy on him. Watch the system do energy on Kevin. Push. See where we're coming from?
Mm-hmm.
So yeah, he's pushing this way,
But it's pushing on him.
but it's actually pushing him and moving you. So that's where we get the positive negative idea. Let's talk a little bit more about work very quickly. So we're going to expand this formula to say delta E equals work, and that work is equal to the force times the distance that it moves. Now what does your AP formula chart say? Force parallel.
Mm-hmm.
Does it have D? Or does it have delta X? That's D, okay.
And
So-
there's another one that says F D cosine theta.
Okay, yeah, that's no big deal. F D cosine theta. So it's just sort of like if you have a regular situation, okay, where you have a box and you're putting a force on it and it moves distance D, moves from here to here, then we would say the work that is done on the box is this force times that distance, okay? Now, if your force was at some angle and it still moved, you know, some distance D, what they're calling force parallel on your AP formula chart, they mean is the component of the force vector that is parallel to the displacement vector. Okay? Now, 9 times out of 10, if you have angle theta, we all know that the x component is the hypotenuse cosine theta. That's where this comes in. Now they should have wrote F cosine theta times D, but it's did they write FD cosine theta?
Yeah.
Yeah, they should have switched around. That would have made more sense. That F parallel equals F cosine theta. But anyway, that's how it is. So, units, what are the units of force?
Newton.
Newtons. Units for distance? Meters. So, the units for work are a Newton meter. And 1 Newton of force to move something 1 meter is what we call 1 joule. So work, energy measured in joules. Both work and energy are the same thing, since by definition work is the change in energy. All right? They're not going to show you this, but we've got 1 minute left, and I'll show you this one last thing. It'll help you out with the homework. There's one more aspect of work that you need to know about, and that is come on now. No, they're not going to get it for us. Oh, there we go. That on a graph of the force versus distance, say you give a constant force and then you increase the force, okay? The area under that graph is the work done. So the area under the force versus position or distance graph equals the work done. Now notice that's different from what we saw last chapter. The area under a force versus time graph was the impulse. Alright? So, like I said, at the beginning of the school year, part of physics is knowing what the area and the slope mean on these different graphs. And like, how do you get that? How do you know it's the area? Well, okay. What if it's just a rectangle? This force times this distance. See what I'm saying? Force times distance. So, if it's constant, then that's what you get. We'll answer those last 2 questions next time. We're looking at Monday. We're going to have a lab dealing with work and energy. And then Tuesday and Wednesday are going to be quizzes. Alright, team quizzes. You'll need to bring your physical textbook. We'll make it open notes, but not open matchbook. So, team quiz, no free chat.
We also have quizzes.
We have
Monday.
free cal quizzes Monday, but the physics quizzes are Tuesday, Wednesday, so that way you don't hammer too hard.
Okay, do you know what they were over? I know you said-
Momentum and impulse on one of them, and conservation of momentum on the other. Go ahead.